Alright, so we're here at the Kerbal Space Center now, and we've got Valentina Kerman piloting our research aircraft along with Bill and Bob, Bill being the engineer and Bob being the scientist, who are both along to monitor our experiments, which are in our service bay here. We've got 2 thermometers, 2 barometers, one backup for each, of course, and we also have this device here, which will sample the atmosphere. And we're going to travel up to the mountain range to the northeast of the KSC. So we're right here right now around the equator. We're going to travel up here to this mountain range where the mid-latitude jet is particularly strong due to the temperature contrast between the mountains along the coast here and the warmer ocean waters to the northeast. And we're going to demonstrate some of the aerodynamic and thermodynamic effects that weather has on a flight in Kerbal Space Program. So let's take off, and then we will jump ahead. When we're taking off here, the wind actually affects the aircraft. So you can see here, the wind right now is out of the northeast, which is coming from this direction, and it's pushing our tail to want to turn our aircraft towards the left here. So we need to apply some rudder on takeoff to counter the effect of this crosswind, which we see here. Once we get to speed, we can lift off here, and gear is up now. So yeah, so as we fly, you can actually see the changes in the weather. You see temperature decreasing as we get higher and pressure decreasing as well. You see changes in cloud cover as we move spatially, as well as changes in the wind speed and the wind direction. So what's really neat here is that as we begin to fly into the wind here, so I fly to the north-northeast here, so you can see the wind is out of 32 degrees, 30 degrees north here. So you'll notice here how our headwind and crosswind components will change as we align more with the wind. So I have to move a little bit further to the northeast here. We want to align it up to 28 degrees or so. There we go, a little sharp. And now you can see we're flying almost directly into the wind. We have a headwind which is almost equal to the wind speed. And what you'll notice here is that our ground speed is actually lower than our true airspeed because we're flying into the wind. So the speed of the air is actually faster than our movement along the ground. So we're going to head north, as I mentioned. We're going to go towards the northeast now, and we'll climb up to about the jet level. And when we get to the jet stream in the mid-latitudes, we'll resume this recording. Okay, so we are now around, let's see here, 25 degrees north, which is in the midst of jet stream, a particularly strong jet stream on Kerbal. If you recall from our poster presentation, there's actually a bit of a bifurcation of the jet. This is kind of a southern portion of the jet that passes over this mountain range here to the northeast of the KSC. So we're currently flying directly into the jet stream. And you can see this because our true airspeed is considerably higher than our ground speed. We have a headwind of around 57 meters per second. That's a very strong headwind. And our airspeed is around 230 meters per second, where our ground speed is significantly lower, as you can see here. So one of the neat things that you can see about this is that as we turn around here, if we go in the opposite direction, you'll see our ground speed speed up significantly. We'll also likely be able to approach a higher Mach number. You'll note here that the speed of sound is 299.17 meters per second, which is a function of the temperature and pressure. If we turn off weather, you'll see that our aircraft will accelerate rapidly and that the speed of sound will likely change. So there we go, we've turned off weather. Now this is just the default conditions in the game. The pressure is a lot lower because the scale height in the default atmosphere is different. It's a bit smaller, and the speed of sound has decreased as well. The temperature is also changed. With KWP, the temperatures are a little bit warmer, as you can see here. Our aircraft's now accelerating because it no longer has a headwind, so it will accelerate quite a bit, actually, if you speed up time here. And it can get to a pretty high velocity. So you can see how the effect of weather changes the dynamics of the game here, because in the absence of weather, you could fly in any direction you'd like, and you won't encounter any wind, so it'd be no problem, and you can reach fairly high speeds, and with sufficient engines, you can overcome the sonic barrier. So I'm going to turn weather back on here, and you'll see us slow down quite a bit in terms of our ground speed. Our airspeed will also decrease because now we have more air resistance. You can see here that our lift-to-drag ratio has changed. Right, without weather on, the total lift is a bit higher. When we include weather, the lift and drag change slightly. as you can see here. There's less drag when there's no weather. When there's weather, there's more drag because we have wind that we're flying into. All right, now we've turned our plane around and we're flying in the opposite direction. Bob Kerman is quite pleased at that. We have quite a strong tailwind now, with a tailwind of around 56 meters per second. And you can see that we're rapidly accelerating in terms of our ground speed. Our ground speed is now far exceeding our airspeed. So consequently, there's actually less drag because now we have a tailwind. But the lift has also changed as well, right? Because we have a tailwind, there's less lift. Because lift is generated by air flowing over the wings. And if we have less air flowing over the wings because we're traveling, our airspeed's lower, lift will change as a result. Now what's interesting here is that you see that our Mach speed is increasing quite a bit. And now that we have a tailwind, the reduction in drag actually is allowing us to overcome or approach the speed of sound, which we're about to here. So now we're actually able to break into the transonic region because we had a lower amount of drag in the lead up to Mach 1, which allowed our engines to overcome that initial barrier. So we're not able to get much faster than Mach 1. We're kind of stuck in this transonic regime because of the fact that, well, as you get faster and faster, drag increases quite a bit, and it's nonlinear, so it's harder to go quick. So now in the absence of weather, what you can see here, now that we've kind of crossed this mountain range, there's no weather, we've toggled off KWP. We've reached kind of a steady speed of around 266 meters per second, or about Mach 0.9. So we're able to go faster without weather than we are when we're flying into a headwind, but not as fast as we are if we have a tailwind. So this is one of the reasons why aircraft in the real world, you like to fly along the jet stream or with the jet stream so that they can get benefits to fuel efficiency and they can travel at a faster ground speed and get to the destination sooner. It's one of the reasons why flying west across the Pacific takes longer than, say, flying east, and the same is true for the Atlantic. So before we go, let's toggle weather back on, and let's do some experiments here. Let's look at what the pressure is here. So here's our pressure display, 25 kilopascals, or around 250 hectopascals, which is where we're at right now at 10 kilometers. And we can see at this altitude temperatures are fairly cold. There's not a lot of cloud cover above us, which is what this is measuring here. And visibility is pretty good because we're near the top of the troposphere here. And we have a really strong tailwind, again because of this large contrast in temperature between the mountainous terrain here and the warm ocean. So with that, we'll fly back to base, and that concludes our little excursion riding the jet.